Welcome back. Now, today we are going to talk about identification of univariate time series models. This is the first part. First, a brief introduction. Then we'll go back to talk about how we estimate the autocovariance and correlation functions, where we looked at the theoretical properties last time. And then we'll say, well, how can we use the sample autocorrelation function and sample partial autocorrelation function for model order selection, which is the next. And finally, we'll focus on validation, because if the model is not, you can say, validated, we should not use it. So, first, model building in general. What we know is that we have some theory, we have some physical insights. Then we often, at least in relation to time series analysis, we have some data. Then, based on some indication of what could be meaningful, then we can estimate parameters in the particular model that we specified up here, and then we can check if the assumptions for that models are fulfilled, and if they're not, hopefully we learn something so that we can go back and try to come up with an idea for another model structure that we can then use. If it is okay, model checking, then validation, then we can use the model for predictions and simulations and whatnot. So this is something that we'll get back to and specify. This is the overall framework we're going to use for the remainder of the course, how to do model building. So as we discussed last time, when a process is mean ergodic, that means that we have, from just a single realization, we have information about the entire distribution, expectation at least. So what we have to deal with, if we restrict ourselves to a Aviva model, then given some data, how do we actually identify which model structure is appropriate? Now, given that, next time we will look at how to estimate parameters, and what else do we know that can help us out here? So one thing we looked at last time was to look at correlation functions related to Aviva models, and that's also where we're going to get today. So last week we looked at the theoretical properties of the autocovariance function. Now we're going to look at how to estimate it. So the estimator is very similar to the theoretical, not surprisingly, I guess. What we look at is in the theoretical point of view, what you have is the gamma of k is the expectation of, let me use a notation like this one, it's the expectation of yt minus y, and now use y bar to use the same as on the slide, which is the mean value or expectation, multiplied by, so we're assuming that it's a stationary process, y t, and if it's stationary, I can just pick a positive value here for k, minus y bar. So this is what we did last week, and what you can see is that it's very similar to what we have here. At least for the inner part is the same. There's a numerical absolute value here, but we also saw last week that the autocovariance with a positive and negative sign in a number of steps is equivalent. So that's just a technicality for calculation. The big difference is that to do the expectation, what we'll do here is to do the sum from 1, not to n, but to n minus k. Because we don't have an infinite sequence, we only have to restrict ourselves to be within those observations that we have. So we have, in order to look at observation yt plus k, we have to have the last one being n minus k, so that this effectively becomes yn. So that's one part. But then you can say the surprising thing is to have 1 over n here and not 1 over n minus k. We'll get back to that in a moment. So, as mentioned, going forward, backwards time is the same. So, it's enough to consider positive values of k. And to get the autocovariance in R, you can use the autocorrelation function and just say that the type should be covariance. So that's fairly simple and straightforward. Now, this estimator is non-central because, as mentioned before, we're using 1 over n as estimator, and that gives us this multiplier on the theoretical expectation for the covariance function. Asymptotically, when n goes to infinity, however, this goes to 0, and thus we are converging in expectation to the true autocovariance function. In practice, we hope that n is large, so it's not a big problem in practice. The reason why we nevertheless use 1 over n and not something so it's unbiased is to ensure that the covariance structure is always positive semi-definite. In case we just divide by n minus k, then there will be cases where you effectively get a correlation that is greater than 1, which should not be the case. And keep in mind that these estimators, they are correlated themselves. So if you see weird patterns at high lags for the correlation, we looked at sample theoretical last week, then you should keep in mind that maybe it's just noise. Now, so if you have a non-stationary series, how does it happen? How does it behave when we look at this covariance function? It could look like this. So to do a simulation, what I'll do is to use the function Aviva.sim to simulate a model. I will specify an AR1 model with a differencing of 1 as well, so a so-called Aviva 1, 0. I will simulate 500 observations, and they look like this. Now, the next thing is to calculate the autocorrelation function for this data, and we see, as in the slide before, that it goes very slow towards 0. So this is what to look for when looking for something that is non-stationary. It doesn't converge to 0 within a meaningful time point. And if we do this, not just to whatever lag is the default, but go all the way out and don't do this in practice, well, you see that there's a lot of correlation all the way out. The reason why it goes to 0 here is exactly as we saw in the slide before, that we do divide by 1 over n, which means that when you go towards n, you have only one element in the sum, and you still divide by as if you have n elements. So that's another reason why you only want to use a certain fraction. There are some practical cases where you need to go up and use a large number of lags relative to your amount of data, but then you should be aware that this denominator 1 over n is there instead of what you would think, so you should not trust things too much. I'll get back to the blue lines here that indicate what is the uncertainty or expected at random. Now, to give you a little bit more, if we simulate the same model, but with d equals 0, then we look at something that is much more stationary, just from looking at it as well. Maybe you should just go back and look at the plot before. This is the non-stationary solution where you can see it kind of drifts and moves around. And if we plot the autocorrelation function of the stationary variant, you can see it goes very quickly to 0. It goes exponentially to 0, as expected. And if we do the partial autocorrelation function, it's not defined like 0 because then there are no observations in between. If you go to lag 1, here we get a signal, and from lag 2 and onwards there's nothing. We'll get back to why this means that this is an AR1 model. Now, if we take the original data, simulation 1, and do the 1 lag differencing of that, then we can plot that as well. then we look at not some non-stationary thing, but a stationary thing. And again, if we look at the autocorrelation function of this, we see that we have something that goes exponentially to 0, and the partial autocorrelation function is again only information in lag 1. So just for reference, if we do the autocorrelation function of 100 normally distributed random variables, then we see that we have, of course, something in lag 0. Per definition, you're correlated with yourself, coefficient 1, but all the rest are zeros. So that's what we are aiming at when we say we want residuals to be IID. Now, in order to estimate parameters, we'll get back to how this works in practice next lecture, but we use a function called Aviva to do this, get some data, and you specify the order that you want for that model that you want to estimate. And here I'll use the so-called maximum likelihood method. And let's just see what we got. Here we estimate MA, AR2, D equals to 1, and 1 MA part as well. Now, if you look at the coefficients that are estimated, then we have the AR. First row here are the actual estimates, and the second row is the standard errors of those estimates. And there's one thing to notice there. Just think of things as being a normal distribution. If the standard deviation is greater than the estimated value, the likelihood that the estimate is actually 0 is fairly high. That holds for the MA1 part. It also holds for the AR2 part. But the AR1 part here has an estimate of 0.8 roughly, and the standard error is 0.5 something. But typically when we talk about a 95% confidence interval, what we care about is roughly 2 times the standard deviation. So in this case, all parameters are insignificant because we are estimating a model that is too big. So let me just copy this and reduce the model order. I always go about and remove the term that is least significant. In this case, it's the AR2 part. So I will estimate an AR1 model instead. You can say this is part of the validation of the model, but here we just do a little bit handheld. Now the MA1 estimate is same order of magnitude as the standard error. It's actually a factor of 1, whereas the AR1 parameter is highly significant. So it means that effectively the appropriate model is to remove this MA part as well. And if we do that, we get an estimate here of the AR coefficient to be 0.64 with a standard error of 0.03. And now if you say 0.64 plus minus what is effectively 0.07, 2 times standard error, which is effectively 0.07, then the true value of 0.6 is nicely well within that range. So we're happy. And the estimated sigma is very close to unity, which is the value that was used. To diagnose these things, I'll just show you examples. I'll get back to more details about it in the slides. Let me just zoom in on this one. We have at the top the standardized residuals. We just normalize by the standard error. Then we have the autocorrelation function of the residuals, and what we should want is what we have here exactly, a white noise signal where only at lag 0 is the only place where it's outside these blue bands here that indicate a 95% confidence interval for the autocorrelation if it is white noise. The last one here is the so-called Young box test statistic, where you look at the first one is testing the first autocorrelation at lag 1, and you're looking what if you include information up to lag 2 and lag 3 and lag 4. So if you include information up to higher and higher order from the autocorrelations, do you get anything that is significant? And here they are all above the 5% level, so we have nothing here. Now there's one thing that I won't comment too much on in the lecture, but I just want to show you an example. It's a so-called cumulative periodogram, where we look at the residuals from the model, and then we have the frequencies down here, and then we say if we have a white noise signal, then we know that all frequencies are equally represented. So that means when you have a frequency distribution down here and you cumulate the contribution to each frequency, then you should be within some range here, which is defined by the blue lines in this case. So here everything looks nice. Just to show you an example, I will show you for the original data. It's actually hard to see, but it's very small frequencies out here. It is very overrepresented, and then it kind of flats out because there's nothing from the high frequencies. But if you go back and remember how the data look like, let's just plot it again. Well, we have a low frequency trend or oscillation, whatever we should call it here. So it's no surprise that we get that. Now, when doing simulations, we also have to kind of look at different kinds of models. If we want to simulate, say, a seasonal model, a seasonal AR1 model, season 12, then the estimator sim function doesn't help us much because it requests us to have a polynomial b and not in some seasonal b to s power. So in order to do that, we just have to construct the appropriate polynomial. So what we have here is repeating a 0 11 times and then have 0.6. So we have 11 zeros and then a 0.6. So that is effectively a 12th order polynomial where the first 11 coefficients are 0. So that I can use to simulate with. And if I plot it, well, it looks pretty much like a white noise signal again. If I look at the autocorrelation function of this one, I see an information, of course, like 0 is always 1, and then I get in like 12 and like 24. And actually I would like to go up further because I want to look at some seasons. So I will go up to like 50. 50 is still much less than 500. And then I can say, well, besides the ones I saw before, I also have a signal at 36. And then you can discuss whether there is something out here at 48 which there actually isn't with a particular sample size or particular sample. Just for simulate again, and then I plot it again, you can see that some things change, and you see that there are some apparently significant lags that are negative down here. So there is some noise in here. We can also look at the partial autocorrelation function, and here the default is again to go up to like 26. We see a signal only in like 12, and if we increase the order up to go up to 50 again we see that the strongest signal is in like 12, there's something in like 30, but it's effectively like 12 that gives us the most information. So in order to make a model that fits this data, we should figure out which model has a partial autocorrelation function signal in like 12 and an autocorrelation function sequence signal in, I think I added here, 12, 24, 36, and so forth. And in this case, we know the true parameters. This is what we did last week, was to calculate the expected values here. And we can see that, well, in this case, we get some estimates that are just below, but same order of magnitude. So that was a little bit of code. I will share the code later. So what did we just learn in the code? We said something about the sample autocorrelation function, and we get it by normalizing the covariance at like k with the variance. If we have y noise and k is different from 0, then the expectation is 0, as we also saw from white noise, and then we have a variance that is 1 over n. It comes from a sum of expectation of a sum of a lot of random variables that are normalized, standard normal distributions, and that gives us a bound of plus minus 2 over square root n. So we have to double, or have to have 4 times more observation to half the width of the interval here, deciding when it's not possible from a statistical perspective to distinguish a value from 0. And as I just showed in the code, you just use the ACF function and the partial autocorrelation function. Basically what you do is to solve the so-called Joule-Walker equations. I'll get back to that when we do the actual estimations. You have them, say, in equation 581. It turns out actually here again that plus minus 2 times 1 over the square root of n is also appropriate as a kind of confidence interval in case the signal is actually white noise. And you can either use ACF or PACF, and you actually don't need, for PACF, you don't need to enter type like I did in the code. I also skipped that as well.